Hello, everyone. I would like to welcome everyone to our product showcase presentation, Thermally Broken Shelf Angles. It's organized by New York Passive House and presented by Faro. I would like to thank Faro for your support of New York Passive House as a sponsor, and we are very excited to have you as a partner. Faro provides innovative products developed through decades of research, development, and engineering expertise, and it will show in today's presentation, so stay tuned. It is my pleasure to introduce Adam Kimball, who is the sales director at Faro, and Michael Russ, who is the senior technical advisor moderating today's session. So please take it away, guys.
Great, thank you very much. So thank you everyone for joining us today. We're excited to present strategies and components to create energy efficient masonry wall assemblies. My name is Michael and I'm one of the engineers at Faro, and I will be moderating the presentation today and responding to questions via the chat feature, as mentioned. I'm pleased to introduce Faro's speaker today, Adam Kimball. Adam oversees the sales and marketing of all Faro products throughout North America. He holds degrees in both civil engineering and business and brings more than 20 years of senior experience in innovative construction products, particularly focused on concrete, masonry, and thermal performance. A little bit about Faro really quickly. We were founded in 1985 by a group of structural engineers with a focus on innovative facade products to improve the thermal performance of wall assemblies with the view that demand for energy efficient facades requires continual innovation. Faro's products were designed to meet energy and thermal performance standards decades before those thermal performance standards became critical in building design. We offer a range of high performance facade connections. However, today we'll be focused on thermal brackets that offset shelf angle supports for masonry and stone veneers. If we run out of time for any questions, someone from our team can reach out via email with the information that you've requested. In the meantime, I'll be answering questions throughout the chat feature throughout the presentation. And thanks again for taking the time to join us. And now Adam will take it from here.
Hi, thanks, Michael, for the introduction. And thank you all for attending today. Again, my name is Adam Kimball, and I'm the sales director here at Faro. And we look forward to speaking to you today and presenting our products about our offset shelf angles known as fast brackets. As Michael mentioned, we are a masonry and facade connection company that focuses on the envelope. And so our company started in 1985, primarily focused on masonry. And throughout the years of innovation, we've created other products that have grown in from not only our masonry ties, but our offset shelf angles, our breakaway fire release connectors, and we do quite a large amount of engineered solutions that are for stone veneers, for other facade connections such as aluminum panels, in addition to siding, your common siding. So please feel free to visit our website after the presentation at farocorp.com, where you can see all the solutions that we can provide for your facade connections. So today, as Michael mentioned, we'll be talking about our fast brackets, and this product has been growing a lot in popularity due to the requirement for continuous insulation, the new growth in the need for meeting the standards across North America, the different provinces in Canada, and as well specifically in New York, where you have to actually model and have a specific psi value for your angles, as well as other locations. And so this is what we do as a company. So not only are we just a product manufacturer, but we're an engineering company in the right that we provide engineering solutions. We sign and seal our drawings, and we're vertically integrated. So everything from engineering down to manufacturing, all the way into the galvanizing of our products into your job site. So we're a vertically integrated company, which helps provide quicker lead times and production for your job sites. So this is important when you're working with a company that can provide these things, not only from a technical perspective, but also from a manufacturing perspective. So today we'll talk about the current challenges with designing efficient masonry wall systems to meet the demands of expanding energy codes and guidelines. So as I mentioned, May of last year, in the midst of the pandemic, there was a new energy code that was specifically for New York City. And this new code requires to model every specific location that would be a thermal bridge. So if you think about the locations that we would commonly encounter, you would have parapets, and then coming down the wall, you would have your shelf angles, which we'll speak about today, balconies as well, and other locations. And so there's specific psi values that you have to put to make sure that you achieve in that model. And so this is where our company's been growing, but this is really now a requirement. So this isn't a good general practice, it's a requirement for New York City. And I think that's a really an interesting opportunity for Passive House to continue to grow as well. And these codes are not only for specific places such as New York City, we're starting to see those codes continually change throughout different locations, but this is what we'll focus on here. An energy efficient shelf angle design. So brick is inherently an energy efficient veneer. So if you think about clay, you think about the primitive buildings that were constructed in the earlier eons of our lives. So we have clay buildings that we can acknowledge in Africa, the ones in the Southwest here in the United States. And these are great thermal flywheels is what it's called. So it absorbs the heat through the sun in the day, and then it transfers it into the evening and back into the dwelling locations as the nights become cooler. And so that's great. And so we've also, designers are increasing their insulation thicknesses. So based upon code requirements or a specific energy code design, designers are increasing their insulation. So the problem is that larger wall cavities require larger shelf angles to support the brick veneer. And larger shelf angles create a number of issues and challenges for designers, which we'll cover. Those are thermal bridging. So shelf angle directly attached to backing creates a thermal bridge. And so thermal bridging is a very simple mathematic formula to determine the effects of thermal bridging. It's the surface area multiplied by the mass. And so what we have here in our condition, so the surface area here is the angle itself is going along the whole perimeter. And then we have a steel, which is the largest mass material that we would use as a construction product. So here we have, when we think about the construction materials that we use, wood, relatively low mass, which equals a relatively low thermal conductivity. Then concrete as well, moderately mass, but and which is equaling a moderate thermal conductivity. But ultimately, steel is the highest thermally conductive material that we have. So if you take that formula that I put out is presented of the mass times the surface area, we create here a larger thermal bridge. And so when we introduce our insulation thickness here, this angle ultimately gets bigger and is ultimately going to be creating a larger thermal bridge. Also difficult to install, so larger wall cavities require large, heavy, and hard to install shelf angles. So as we can see here, which we'll review, conventional shelf angles cannot adjust easily to meet construction tolerances, making them difficult to install and require additional labor. And lastly, it's expensive. So we're all familiar with the price of construction materials going up. And so this is steel weight is always going to be affected by the price is going to be affected by the steel weight. And so ultimately here is the things that we're going to create, and we're creating a problem as we're designing with masonry. So we'll focus first here on thermal bridging. Here's a thermal model. And so what ideally we would like to see here is we would like to have these gradients here in our insulation plane. And so we can see that happens here at the masonry tie above. It happens here nicely through our through-wall flashing. But then we get here to the angle, and due to the size of the angle, the thickness of the angle, as well as its surface area, we're getting a large thermal gradient here that's actually happening here in this thermal model located here in the CMU wall. And so this is what we're creating by reducing the thermal comfort of our floors. We're also reducing the thermal efficiency of our buildings. And so this is what we can see and feel, especially in colder climates. But one thing to acknowledge is the magnitude of heating energy loss in colder climates and cooling energy loss in warmer climates is virtually the same due to thermal bridging. And so while you can't feel it in warmer climates or warmer days, such as New York City, it's still losing the same amount of energy efficiency. And so this is why it's important to think about these details when you're designing a masonry wall. So you say, okay, Adam, well, that's just a therm model. What happens in real life? And so here's a therm photo. And so we here have located at our parapet walls, and here are located at our windows. where we can see that this is our benchmark. In a therm photo, the whitest locations are the hottest. And so now we can see here at the same perimeter of the walls here, we have our shelf angles that are also yellow to white. And so this is creating the thermal bridges, reducing the effectiveness of the insulation, leading to greater energy consumption. In commercial construction, thermal bridges are formed by brick ties as well. And so you say, Adam, well, why don't we see the brick ties? And it goes back to that equation that we've discussed, is that the masonry ties, albeit they're 16 by 24 on center, so it's quite a lot of surface area. What we see here is that just the mass is not there. So masonry ties that we manufacture, for instance, are 16 to 18 gauge thick, high depth galvanized carbon steel. So the mass is not there comparatively to where we can see here in our shelf angles. So continuous conditions such as the shelf angle present a much higher potential energy loss. And so this is why we want to focus on really smart designs for our thermal brackets at these locations. Here's a photo of from RDH, which is a leading building envelope consultant, and Dr. John Straub that presented this. So envelope consultants go to these people to get more information. So these are the people that are the experts upon the experts in this field. And so what we have here is the good, bad, and the ugly. So we'll start with the ugly here. And this is a building that was built maybe in the ones that we grew up in as a kid, or the ones that were built pre-1990s, where we had insulation within our studs, but no insulation here to the outside. And we had a 4x4 by quarter-inch angle located here. And so the bad part, the ugly part about this is that there's a lot more thermal bridging that's happening here at these locations rather than the thermal bridge that's located here at this small angle. And so we move forward where we try to fix this, where we're providing continuous insulation here on the outside, but we now are introducing a larger angle. And so this larger angle is gotten bigger by thickness and also by length. So now it's commonly we would see a 4x7 by ½ inch angle. And so now the mass and the surface area is grown based upon the dimensions of the angle. And so while we've gotten rid of the thermal bridges here located in the studs, we've created a larger thermal bridge here at the shelf angle itself. And then we move to the good, and ultimately where we would like to meet peak performance is here. And so we still maintain our continuous insulation. And so now we have a thermal bracket where the insulation is going through the bracket itself, and it's only having a punctual thermal bridge at certain locations. And then we're mounting this to a 4x4 by quarter-inch angle. So we're reducing the mass and while also reducing the surface area. And this is a really fundamental way to reduce the thermal bridging at these locations. So installation challenges, we're actually getting more and more contractors actually coming to us after they've used our product and using fast thermal brackets as their VE option. So they're actually saying, hey, we don't want to install conventional angles any longer. We would prefer to install fast thermal brackets. And so while 4x4 by quarter-inch angle is light and easy to work with, large cavities require larger and thicker shelf angles to access support at a greater distance. So if you had loose lentils over your home construction, you would just be using a 4x4 by quarter-inch angle, especially here in warmer climates where you don't have continuous insulation on the outside of a building. And so that's only 6 pounds per linear foot. And so you think about 10-foot sections that masons commonly would want to use, that would be a 60-pound per 10-foot length. In New York, we commonly see 4x7 by ½ inch, which is 17 pounds. So we're 3 times heavier than a 4x4 by quarter-inch. And so this is 180 pounds per 10-foot length. But we've seen it up to 8 by 8 by a full inch of bent steel that is being used, and that's 51 pounds per linear foot. We've seen it, and we're not trying to provide any shame for anybody that's ever specified something like this, but shame on you for doing this to the masons, because this is quite heavy to pick up and hoist. It's a difficult solution to try to actually lift up there. And by doing things like this, we're actually just adding cost to the building, not only the steel cost, but the labor cost to install this. And so you think about getting it lifted up. then it's trying to drill it into the slab itself, and providing these extra costs. So you think about lifting a large angle up there, the cost of welding or drilling these holes into the shelf angle, coupled with the rebar here. So imagine if you get a 51-pound angle up there finally, and then you have your holes that are drilled 2 foot on center. And then, so you're drilling a hole through there to hit to your, to get it anchored into the slab, but you hit rebar. Oh, okay, so now you have to drill through that angle again. Here, somewhere 3 to 4 inches to the side of it. Now you through that 1 inch angle or ½ inch angle, and hopefully you don't hit it rebar again, but you're continually having to figure out how you can anchor this in, all the while trying to hoist this up generally above laborers' heads. Then that turns into the larger the angle, increases the requirements of the anchorage. So increasing the amount of anchors or increasing the diameter of the anchor itself. So this can also additionally increase costs. Size and weight of shelf anchor results in additional costs for the labor and the equipment to actually hoist this up. So in the past, these things weren't necessary, but now they're having to have come-alongs or pulleys or hoists of some sorts that actually lift these up to the face of the slab and then install them. So larger shelf angles are more expensive, and I can tell you considerably more expensive, especially these days as steel prices are going up in the United States and Canada of over 30%. So material costs and difficult to source. Also, it becomes a question of quality control as well, because if you beyond 4 by 7 by ½ inch, it's usually going to be bent plate, and bent plate is okay until you start to actually bend it, because not many fabricators are taking bent plate, bending and then galvanizing it. So if they're taking galvanized bent plate and then bending it at the seam, they're actually creating a weak point in the steel and reducing the galvanization at that location as well. All at its most critical location here at this corner, where the strength, the weakness of the strength is that of the steel is located. And then because of this larger angle that we're specifying, we also have to require lip brick, because our bed joint reinforcing is only 3/8 of an inch. This angle being ½ inch is greater than that bed joint. And so we have to either cut back the brick sheet to hide the angle itself, or buy lip bricks from the manufacturer. And the premium to buy one of these bricks or have a mason cut these bricks is $2 to $3 per brick itself. And so these are all the things that you're coupling in by specifying conventional angle. So when we're getting prices back and we're over budget, this is a very clear location where we're saying, hey, this is how we can help solve this problem by just getting rid of these large angles that we're trying to support over near on. So the solution is thermal brackets. And so before we get into the presentation, I thought it was important to talk to you about what you should expect from a manufacturer. And so at Faro, we maximize value for our customers by collaborating with architects and engineers at the earliest stage. Architects generally ask, well, when should we get involved? I always say that design development is the primary place. Early construction documents would be okay. In DD phase, that's when we can actually provide you CAD details that you can put into your drawing sets that are sizing the brackets, that for heights and depths, giving you the ultimate efficient spacing of the brackets, and giving you just the nuances of how to use our product most cost efficient and most thermally efficient way. You can leverage our expertise. We have, as myself and Michael, we have other engineers, a total of 5 on our staff, as well as CAD drafters that are doing this to support the design community. So we're reviewing drawings at design phase, designing and engineering custom ties as well with large cavities. So we provide, and so we're optimizing those layouts, supplying sign and seal drawings. So we're taking on all of the sign and seal drawings. We're taking all the delegated design from the anchor to the angle. So that's what the scope generally that we would take into our package is the anchor to the angle. So a team of structural engineers provide unparalleled customer service. So when you're calling it to us, you're not calling it to a customer service person, you're actually calling, and if it's not It's generally one of our engineers that's going to be responding to your inquiries. So this is one-to-one customer satisfaction that we're trying to maintain. And I don't think you should expect anything less from an engineering company that's manufacturing masonry accessories. So onto the brackets. So proprietary structural thermally broken shelf angle support. So continuous insulation behind the shelf angle. So now, as you can see, the insulation is no longer on the angle, it's actually behind it. Your insulation is within the pocket of the bracket that you can see here. And so this is the offset shelf angle from the structural backing position. At the shelf angle remains fully outboard of the insulation. So we're providing a punctual thermal bridge here, whereas the linear thermal bridge is offset from the insulation itself. We also, to improve the thermal efficiency, so if you're familiar with our products, just 2 years ago, we officially launched our improved thermal brackets with proprietary hole patterns. It's a truss model. So the bracket itself doesn't have any reductions of structural benefits or structural integrity, but it increases the thermal performance considerably by reducing the superfluous steel out of the bracket itself. And so these can be manufactured, as you'll see further in the presentation, at any depth and any height. Currently, one of the projects that's wrapping up in New York City, the brackets are at 18 inches in depth itself. So get to really some outstanding depths, and it's a matter of engineering, and that's why you can rely on us to support you in that. So thermal performance. So as you can see here, smart, cost-effective, thermally broken shelf angle design. So here's our psi values and our U values. And so we have here our effective R value is 0.525 as a conventional U value, and then our linear transmittance 0.583. So this angle here is a 4x7 by ½ inch angle. And so as you can see, our insulation's here on this, and by using a fast bracket where our insulation is now between the angle itself and only having a punctual thermal bridge, this bracket here is made by 3/16 inch steel and reducing all the unnecessary steel, and spaced at 4 foot on center with using a 4x4 by ¼ inch angle. We get to a U value of 0.34 or a linear transmittance value, a psi value of 0.095, which is well below the required New York City performance guidelines that are for the energy efficiency at thermal bridges, which is giving us a percentage of a thermal improvement at 83%. So effectively an 84% improvement from your conventional shelf angle. So this is one, again, going back to the contractors and why they prefer to use our products. It's not many times where you introduce a new product to masons and they come back and say, from now on, this is all we're going to use. We're working with some other contractors that have actually had design meetings with the architect and engineer, and the architect has asked the question to the contractor, are you okay with specifying a proprietary product like this? And the contractor said, absolutely, please design with this and get Faro the design drawings. This is what we use from now on. So it's really exciting how the market has accepted our products, and they're willing and ready to use it, from not only from the design side, but also from the contracting side. And so this is the benefits that really the masons enjoy. All of our connections are generally bolted connections. So we want to put our products in the scope and hands of the mason. We want to provide them bolted connections because ultimately they're going to be putting their angle on their bricks on the angle. So they need to make sure that that angle is going to be plumb and level. And that's what we're providing here. And so what you can see here is that we have a slot at 1 3/4 at 22.5 degrees. So depending upon the anchor, you're getting up to 1 inch of vertical adjustability. If you imagine, even if the slab is running high from left to right, you can adjust the bracket by turning it or rotating it. So you're adjusting each bracket individually. Once you get the angle level, then you would tighten all the bolts down, and then that would be how you achieve your levelness for your brick. If the slab is in and out and you need to shim it, we can manufacture these brackets. We manufacture as a standard at ½ inch increments. So you start at 1, 1.5, 2, and so on up to 18 inches. And then any small adjustments, then we would provide shims, and this is included. So we make shims at 3/16. We make them at 1/2 inch, and we make them at 1 full inch as well. So this is how you get your plumb and levelness out of this, out of slabs that are generally out of tolerance, all the while by being bolted connections and not having to worry about a steel erector coming out, bolting angles to the slab itself, not being plumb or level, getting him to come out, which is ruining your construction schedule. Putting this in, we generally see a mason start by putting in the brackets first, having his next crew chasing them up the building, and having his sequencing working very in line and keeping up with his schedule as he planned. Brackets can be made to any depth, as I mentioned, and any heights. So thermal brackets, depth and height, and slot for bolts can be customized to fit all cavity sizes and anchorage. Brackets can be modified to accommodate project requirements at site conditions. As you will see, we have various different types of anchoring types and brackets that can be used for different applications. Height can be extended to support veneer below the slab backup, reducing requirements for costly structural steel, which we'll see. And so other anchoring options, which we'll see, but we see these brackets, as I mentioned, as deep. We've done as deep as 18 inches, and we've done brackets as tall as 5 feet. If you could imagine, if you're doing a high-rise building in New York City, where you have a mezzanine floor and somewhere in the middle of the building for banquet rooms, and you have your floor at a certain location, and then your windows are coming down, and so you have brick that's going to be between that. This is where you would use a brick bracket that's to those lengths of 5 feet. So we'll cover some of those details. So here's our most standard bracket, and this is a bracket that's just 6 inches high at various steps of your insulation requirements. And so you can see this one's just face mounted to the slab, being it post installed with expansion anchors or installed with embeds as well. We don't make any requirements for any types of anchors that are used. We can provide options for anchors, but we don't require you to buy any proprietary anchors from us. As you can see, your insulation is again behind your angle, and then you have your termination bar, and your through-wall flashing starting here at above the bracket, coming over the bracket, and then onto the angle, and then taking the 90 onto your through-wall flashing. So it's a very common detail for if your angle is bolted to the slab that your through-wall flashing would come down and then turn 90. We're just changing the departure of your through-wall to come over the brackets, over the knuckles themselves, as you can see here. And you can use any through-wall flashing material. The one I kind of like is a company called York. It's a through-wall flashing. It's with a pliable stainless steel. So it's pliable, and it's actually got a self-adhere membrane on the back. There's different manufacturers, but York seems like it's a great company. We have no affiliation with them, but I could recommend this as a flexible flashing that goes over the brackets. Here's a detail with studs, so you can have it with stud walls, CMU walls. We're still anchoring here in this detail to our cast-in-place floor. And so this is an extended bracket. Extended brackets can both come in lentil brackets and standard brackets. A standard bracket that you can see here is that it has the foot that supports the bottom of the angle. Whereas here with a lentil bracket, you have the foot is now in the vertical leg position of the angle to give you that flat profile here at the window transition. Lentil brackets are only used over window conditions where the brick is either too high or the window is spanning too wide. So these are all the things that we would provide you as far as when's the appropriate time to use standard brackets. For instance, if the brick is not too high or the window is small, we would have a standard bracket here in the masonry conditions, and we would span the windows. This is the most cost-effective solution. But then there are certain cases where we would also introduce lentil brackets. And so this is a supplementary condition only when it's required. So as you can see here, termination bar starting at the top with your through-wall flashing going over the bracket as it's embedded in your insulation layer onto the angle itself, and then coming up with your drip flash. So these are now this is the condition where you have brackets that are longer than 25 inches. And again, these are all bolted connections, which is very important, again, to keep this all within the scope of the mason. So no longer are you needing kickers and where sill fabricators are coming out to the job. So it's the same extended bracket. In this case, it's a lintel bracket. So when this bracket exceeds 25 inches in height, here's our back brace. And so this is a bolted connection to the back of the bracket through your sheathing here, where we would have this back brace plate that would be in plane with your sheathing. This would be inside of the track of your studs, where there's a stopper that's on this threaded bolt where you would tighten it to the underside of the studs to provide additional wind bracing for the large wind loads. So there could be a question, well, how do you support the rest of the wall? Generally, your masonry ties are there to provide wind resistance. This is for brackets themselves, when they're this long, we just need to provide additional resistance to wind loads that are on the brackets themselves. The rest would be taken up in your masonry. Also, this is an inverted bracket. This is when you're transitioning from different material bases. So in this case, you could have, for instance, we see this common detail where you have ephes below, and then you would have masonry transitioning to the top. You can additionally do this with aluminum panels, fiber cement boards, etc. And so in this detail, the angle is no longer down where the horizontal leg is at the bottom. It's here at the top now, and it fits inside of this pocket. And so now your termination bar is coming a more traditional path where it's coming down and then onto a 90, onto the through-roll flashing, onto the angle itself. Still maintaining your insulation behind the angle and within the pocket of the bracket itself. And so you have your mortar collection device here, your mortar net, and in between your brick layers. And so you're still maintaining, with all of these details, your air cavity as well as your insulation thicknesses that's being specified. So what are the materials that you would expect from us as a manufacturer? So sander brackets, where we would start here at the bottom, where we would be transitioning from masonry to masonry junctions or spanning windows as possible. And so from us, what you would receive is the bracket, as well as the shims, our square washers. Beyond that, the anchors and the angle can be supplied locally. We can supply it, but again, we want to give this the most cost-effective solution. So typical anchors can be purchased locally. We would specify it in our delegated design submittals what type of anchor to be used, and as well as the thickness of the angle, generally 4 by 4 by 1/4 inch. But these are the things that you would buy locally to make this the most cost-effective solution. Alternatively, when we get to window conditions where if this is required, we would still supply the fast bracket, the shim, as well as the washer. But in this case, you could also buy your anchor locally. But in this, we would provide you this as a system with our punch lintel angle. And the purpose for this is quality control. And so the way that we manufacture this is that we take angle in raw, so it's just bare carbon steel. And in this condition, we take it in raw, we'll punch the holes in this, and then we would hot dip galvanize this. So all of our products that we generally manufacture are carbon steel that we all hot dip galvanize. There are certain times where we would provide stainless steel brackets, but those are very isolated conditions for specific reasons. So on the cost savings, and so this is the time in the presentation where we start to talk about this cost savings. And I know that many people are here in the presentation today that have been in a similar presentation where somebody asked, well, hey, it's a great product, we would consider using it, but how much is the cost? And the person that's doing the presentation would say, take a deep breath and say, well, it's about the cost return on investment, life cycle savings, and that's not a good conversation to have when you're talking to a developer and a contractor. Developers and contractors are worried about building efficiency and sustainability, but as I always say, especially here in the United States, the green that most developers are focused on is the green that's in their pocket, and that's reasonable. And we can't remove ourselves from that, because it is a reasonable thing that they have investors, they have to turn a profit, as all of us are trying to keep our lights on. So they have to make sure that their budget's in line, as well as the sustainability part of it. And I'm really proud to be here at Faro to talk about actually how we actually save money on our product. So from the moment it comes to the site, we save money, to the installation, we save money as well. So there's multiple savings that we actually have. So here we have a conventional shelf angle. This shelf angle is 4 by 7 by ½ inch. Again, this R value here is 10.8, which is reducing your effective R value by 36%. And so the 4 by 7 by ½ inch angle here is, and this is January 2021 prices at $21.25. So if you take the general pricing that's coming about currently at 30% premium, and these prices are skyrocketing. And keep this in mind, these numbers are not seeming like they're going down. So the thicker the angle, the more mass to the angle itself, the more expensive it's going to be. So if you add 30% to this, we're at $28, roughly $28 per linear foot. And this is our condition with a 4 by 7 by ½ inch angle with 4 inches of insulation, which we commonly see in New York. And then if we transition here, and people would say, well, how are you saving money? Because intuitively you would think by adding something, you should be increasing the cost. And the way that we do that is, again, it really just goes back to how we are using our materials wisely. So here we have a fast bracket, and this fast bracket is going to be installed 4 foot on center at $24 per bracket. So that gives us a $6 per linear foot bracket. And then the shelf angle, we're going to be transitioning to 4 by 4 by ¼ inch angle, which is $7.25. So that's $13.25. So if we add 30% to this, so that's 70 cents, so $1.20. So we're at $9. So we're at roughly $15 a linear foot compared to $28. So 13 to 21 or 15 to 28. We're at $8 to $9 per linear foot savings per floor on that building. So think about the buildings that you have worked on in the past or the ones that you're currently working on that are using masonry. And think about the amount of linear feet that you have across the perimeter of the building, and actually just by material alone, how much you're saving. Just purely material, just the angles and the fast bracket with our 4 by 4 by ¼ inch angle. Again, you're also improving your insulation. So R value of 10.8 to an R value of 16.7 here. And so what about drop down conditions? And you say, maybe this isn't a condition that we would see, but we want to see more conditions like this. And then the prices actually even become more apparent and the savings are increased even further. So here we have our what we commonly see as a kind of a built-up conditioning, where you have a pour stop here with the Nelson studs. You have some kind of tube section or spandrel beam that's below it, and you have a welded shelving, a welded knife plate to the face of that, and then your shelf angle is welded to that face as well. And so this is your built-up system, and this built-up system, be it a kicker or something similar to this, from the prices that we've gotten from steel fabricators, this is at roughly $95 a linear foot. And again, this is January 2021 pricing, not May 2021 pricing. So these prices are exploding based upon the cost of materials these days. So again, effectively using, wisely using our steel material, we're going to have a lintel bracket that's over a window here. And instead of having a spandrel beam, you can have a box beam with cold form studs. That's just for boxing out your window rather than having a structural system here. Along with our punch lintel, this solution, we're going to get to $32 a linear foot. So we're at over $60 per linear foot savings. And again, this is just materials that we're talking about. We're not talking about labor. We're not talking about any ancillary costs that you're having to consider when designing with conventional angle. So this is the other things that we have. So here's the ancillary and the kind of the coupling effect of savings that we find. And these are things that are coming from the masons, the contractors that we work with. The shelf angle installation reported by installers can be twice as fast with thermal brackets compared to conventional shelf angle. And so that's both in the installation and also the coordination. So again, all bolted connections. We don't have to worry about a steel steel fabricator coming to the site to install anything. So we're also reducing hoisting and starging large angles on the face of that slab. We can actually get rid of those lip bricks that we talked about previously in the presentation. So that lip brick now has a 1/4 inch angle that's at the bed joint, so it fits quite nicely within the 3/8 inch mortar joint. So we're also saving that $2 per brick savings, and lower cost of shelf angle. So thermal brackets span the cavity, so smaller shelf angle sizes can be used, which also reduces freight of cost at the job site. So think about not only lifting a larger angle, but also the coordination. And you think about carbon emissions, and if we're looking at the carbon footprint of a building, this can also assist in that by using smaller angles. 4x4 by 1/4 inch angle is a commonly readily available angle. So this can be sourced from any providers locally, whereas if you're looking at large angles 4x7 by 1/2 inch or thicker, this is going to have to be either sourced from the mill or from somewhere that's not, and it's not going to be readily available, or they're going to go to a fabricator where they're actually going to bend plate itself. So you're not going to get a nice clean square edge. It's going to be rolled, going to be bent. Quality controls can always be an issue. Again, no welding or drilling in the holes in the angle. So if I was to kind of go back here, so all these holes have to be drilled or be welded, whereas here in the brackets, you already have the slot. So you're just drilling them in or anchoring it to the embeds. So no more drilling into the anchors, to the angle multiple times over because you hit rebar. In the event that you hit rebar with a fast bracket, you just move it over. You're not having to re-drill the bracket. Yes, of course, you're going to have to re-drill the hole in the slab, but ultimately you're saving the time of trying to re-drill through a thick angle and then through the slab again at multiple locations. So we talk about additional configurations. We talk most of the time here in the presentation by connecting it just to a slab and it looking like just standard brackets. Maybe they're extended both in depth and height. But there are also conditional configurations to address the different types of construction methods that we commonly encounter. So here we have the top of thin slab. And so this is commonly used for your thin panel decks. So your EcoSpan panel decks, your Hamburg panels decks, corrugated decks. It's called multiple different ways, but due to the thinness of the slab, we mount to the top. And generally, if they're within the track of the studs that are sitting on top of it, most of the time we see this construction type. If it's a thin deck, it's also got steel studs. So we would mount this within the steel stud of the track. Additionally, we could use this solution for hollow core plank design. If we can't anchor to the face of the hollow core plank, we could also anchor to the top of the hollow core plank or to a CMU wall. We generally see if it's hollow core planks, it's CMU walls, so we can additionally anchor to a CMU backup wall as well. So this is our thin slabs, our standard with steel stud backup. So we can anchor to steel studs. Just needs additional bracing. We see it different ways. There's either stiffening the studs with a bit of a steel angle at the face of the stud. We also see a band going across the face of the steel studs that would be in the transition plane of your sheathing. And so that's the thickness of your sheathing, generally 5/8. You would have a 5/8 inch cross brace that would fit within that, and then the brackets would be anchored to that as well. Also the steel members, so if you had a steel construction, a red iron steel building, and you wanted to hang it to the W sections, so you can hang it to, again, to the flange of the W section here at the top. We also see it where there's welded plates to the front of the flanges here, and you can weld to the face of it. And additionally, hollow tube sections. So we see hollow tubes in steel construction buildings. We see it in situ place construction. So this, where you might have a spandrel beam that you want to connect to due to large spans, for instance, there's ways of connecting it also to hollow tube sections. You could through bolt it or additionally use proprietary expansion anchors for steel, such as a Lindafter bolt. But there's various amounts of different configurations where we can actually install it to different backup systems, be it at the wall or the floor condition. Additionally, architectural effects that we can help use with fast brackets. So this is a double bracket. We've done this quite often, especially in New York recently, where it's a double bracket for corbelling effects. So imagine that you have this over a window, and then the brick is continuing to grow out. You can use, and then there would be another bracket here to have a corbelling look. Additionally, we have fast flex system. So this is a curved system here. So no longer do you have to have square walls. You can actually have your angle match the curvature of your floor slab. And so we use here our thermal brackets, and then we augment the angle to match the profile of it. And to get the specific tolerances at the job site, you can additionally just continue to bend the angle back. This is a specialty bracket, so that the knuckles that go over the bracket aren't fixed. You would put the bracket on first, and then the clips would go over the top of that, and then it would be anchored back to the bracket itself. This is a project that we've used this in, the custom angle supports. This is a project that we've used this on in New York City at 2505 Broadway, if you're walking around locally, where the piers had a custom profile. Again, we used our special brackets here, where there's a clip that goes over the top. They installed the custom angle that we manufactured at those pier locations to match the profile of the brick that comes around the corner and at a curved location, and then steps back to provide this reveal, and then around the other side. Again, so this is all coming from us, so it's a vertically integrated solution. And then we have our concealed lintel clips as well. And so this is a system that we use quite a lot. So if you don't want to see the angles exposed, you could use our concealed lintel clips. Masons really like this, believe it or not, because it's a prefabricated solution, whereas this clip that's hanging on the back of the vertical leg of the angle is segmented here to the clip that's embedded into the bricks themselves. So the clips are installed into the brick 2 foot on center, and they're brought to the site, and then they're connected to the one that's clipped to the back of the vertical leg of the angle, bolted together, and it's a clean solution. We've done this on 378 West End Avenue, if you're walking about, and we've done it on quite a lot of other projects, but that's the one that comes to mind. So again, many different solutions that architecturally, you can actually think beyond what you've done in the past. So 378 is a great example of that, where architecturally, Cook Fox was looking to create different column profiles, but the slab of the floor slab was square. And so this is where our brackets were used at different profile depths across the facade to create those different reveals. Quite a nice project. If you're nearby, please pass by. So we're going to go ahead and, as we're transitioning into comparisons, we always just want to highlight what's the alternatives out there and some of the things that you should consider if you're thinking about these alternative solutions. So these are ad hoc solutions or on-site solutions that we have seen in the past. And so here we have a tube section here welded to the angle, and here is an angle that's bolted to the slab and then welded to the angle. This is we found that it's quite expensive, labor intensive. If this is not done off-site and is being welded, then you're having a weld point that's no longer hot dip galvanized, which is a huge quality control issue. No on-site adjustability. So once if you're getting back into the same problem. If this is already welded and you're hitting an rebar in the slab, then you're creating these problems of moving this over, and how do you move over a fixed elements? And really no thermal performance data. So how do you actually show that this is performing to the energy efficiency details that you're looking for? This is a manufactured solution. So in this manufactured solution, you're having to buy proprietary embeds. This is, again, welded. So this knife plate is welded to the angle. So you're having to buy this as a fixed solution at links that would be shipped generally from Texas. And whereas with our fast brackets, you're buying just the bracket itself. You're getting the angle source locally. And here's a good photo of how the detail of the flashing is going through in this location. These brackets here were 13 inches deep if you're interested. Yeah, and so, yeah, of course, with all the proprietary things being shipped from various long distances, this is actually quite expensive solution, we found. Thermal brake pads. So here's something that people have talked about as far as thermal efficiency and thermal improvements. And there's been quite a lot of studies that disprove this notion that plastic material provides thermal efficiency. So they're more expensive per unit, as the thickness of the thermal pad behind the shelf angle is generally limited to a 1/2 inch to 3/4 inch. There's no reasonable thickness of continuous insulation. So you see here, here's your thickness of your pad. You're still having to specify a really large angle where your insulation is still on that on the angle itself. And if you try to go beyond 3/4 of an inch, where that's where they say there is the thermal improvements, then there becomes structural questions, also fire code questions, because this is a combustible material. Anything less than an inch, and ideally anything less than 3 inches, based upon the studies provided by Northeastern University and the University of Alaska, says there's actually no improvement and could be actually further, even worse detrimental causes by using these pads from an energy efficiency standpoint. So lower load capacities resulting in tighter spacing. So you might have to use these, you would definitely have to have more anchor bolt locations based upon the veneer load, because brick is a heavy veneer, 35 pounds per square foot, and requires longer bolts. So the longer the bolt, the more eccentricity is going to be induced on the bolt, which increases the structural questions of this. So we talk about the effective R value of the material. And so here's the U value of the material. Conventional is at 0.525. Again, our linear transmittance is 0.583. Conventional with a break of these plastic pads assembly is 0.59 and gives you a linear transmittance of 0.40. Actually, which is not below, if I recall correctly, is not below the prescribed number for the New York City Energy Code requirements. And that it does provide an improvement, but it's only 30%. And so with using our fast bracket, we get to a 0.341 U value or a 0.095 linear transmittance value, which is improving the thermal improvements by 84% compared to the benchmark of conventional. And some people says, well, can I double up? Can I put the pads behind the fast bracket? And as you can see, there's really not a lot of juice to squeeze here to improve this further. Our fast brackets are made out of carbon steel, and so this is how we maintain the cost effectiveness. But adding a pad, we're only getting an additional 3% improvement in this. So we really don't advocate for this, because if you we jump to the cost of that. So even with the fast bracket at 3-foot spacing, we get at $21 to $24 per linear each at $7 a linear foot. A 4x4 by 1/4 inch angle at $7, and a Hilti bolt every 3 foot gives us a cost of $16.50. The composite pad, $12 so $6 a linear foot. You're going to need comparatively, you're going to need a 6x6 by 5/16 angle, which is $21 per linear foot, as well as a Hilti bolt at every 2 foot. So that gives you $3 per linear foot at a total cost of $30.38 per linear foot. So while these pads seem compelling because it's a new age material and it's plastic, doesn't seem thermally conductive, as you can see, the performance is not great, and the cost is actually double than using a fast bracket in these locations. So as we're wrapping up the presentation, I'd like to tell you one of the things as part of being a member of the New York Passive House, fast brackets are Passive House certified. So you can go to the passivehouse.org website and look for our certification. Both our masonry ties and our fast brackets are Passive House certified. So you can design with all the confidence in the world that our products can meet the Passive House standard. So if you're designing a building you're going for that Passive House standard, we are Passive House certified. And so you don't have to go through any modeling. You can use our ties and our brackets to meet that Passive House certification. We've done over 1,600 projects across North America. Here's some references in New York, looking to add more with you. And so, yeah, Passive House ties as well, as we're wrapping up the presentation. So we're here just kind of, the reason why we can increase our Passive House certification with our ties, again, reducing the surface material in our ties, but also increasing the surface area where we're actually spacing out our ties greater. So we're just 1 minute short, so thank you for your time, and I'll leave it to Andreas and Michael if there's any questions that we should address prior to the end of the presentation here.
Thanks, Michael, for the presentation. You were spot on with the timing. Fantastic. It was a very good and interesting presentation, and it shows that the technology to avoiding thorn bridges is moving fast, and it's important, obviously, that we include that into our not just design, but also into our architecture thinking. I think there are many more possibilities for architects to deal with that problem. So I would like to open up the Q&A. I think, Michael, you can take those questions from the chat box. You have answered quite some of those questions already. So please take the questions.
Yes, thank you. I think most of the questions have been addressed. Anna, if you could maybe take a quick moment to talk a little bit about some of the flashing solutions that we've been working on and some of the problems that we've been addressing.
Yeah, so that's a great question. I'll try to get back to some of the slides. So yeah, flashing is a great question. I know that comes around quite a bit. So there are let's say the general flashing solutions. I could use this one here. Again, you need a through-wall flashing. What we want to make sure doesn't happen with a peel and stick is that we don't want that peel and stick to be punctured by the knuckles of the bracket. So a traditional through-wall flashing or a pliable through-wall flashing that is made out of stainless, such as the ones from New York, would be ideal. But you can generally detail this properly by having your insulation sitting proud enough into the brackets and then having your membranes coming over this. For larger brackets, that becomes more of a detail that you will be seeing something. So you can see here our insulation is the knuckles of the bracket are within the insulation here up until the very bottom. And if you come to our site within, say, the next month, you'll see some real new innovative things we're doing to actually further prevent any penetrations of your membrane at these locations. And so we're coming up with some really innovative things. We hear the questions and we're coming up with solutions. So stay tuned. Come and see us in a month and we'll have some very innovative things for this location. Thank you, Michael, for that question. So, but through-wall flashing is the best. Pliable or traditional through-wall flashing is the most straightforward detail for that.
Great, thanks, Adam. I think apart from that, we don't have any or too many outstanding questions.
Well, again, thank you so much, everybody, for your time. I appreciate you spending an hour with us today for our presentation. We look forward to working with you. Again, visit our website at ferrocorp.com. You can reach out to myself or Michael or one of our other engineers. So we're looking forward to working with you. And again, thank you. We appreciate the New York Passive House for helping us provide this presentation today. They're a great organization, and I'd like to also just share with you our dealer in New York, Glenwood Mason Supply. They can help you with providing samples and material there locally. Hopefully, past this pandemic, we can provide presentations in person, no longer virtually. So if there is a reason for us to do one for your specific office, we can do that now virtually, or hopefully in the future at your office. We look forward to working with you and have a great day.
Thanks, Adam, for the presentation. Thanks, Michael, for the Q&A, and thanks, Fer, for the presentation. We're gonna stick around for a couple of more minutes. Anyone who has a specific question, you can unmute yourself and just ask the questions. Otherwise, we'll send out the recording as well, and also the contact info of Adam and Michael. Thanks, everyone.